So thank you everyone for coming back. So this is the fourth and maybe the last of this series. Um, I would certainly be glad to come back and speak to you guys again, but I think in terms of creating something that has a coherent sort of syllabus behind it. This is really going to be the conclusion to the story. I haven't been able to produce everything that I wanted to discuss with you guys, but I think that altogether as like a single body of work for further study, I think it's quite it's pretty compelling in and of itself. So we can always discuss things later if we want to return to certain concepts or something, but I'm pretty pleased with how we're wrapping this up. So the in the on rewatching the third lecture, I was a little disappointed in how I handled some of the material. I think that I really wanted to nail certain aspects of concentrated liquidity, and while I think that it was still pretty good, I think that there are some components that I think I could have done a better job explaining. And so in contrast to the previous lectures where I have offered solutions to some of the homework material, instead, I've decided to actually do a full addendum to the third lecture and hopefully really give you a much stronger theoretical framework to understand concentrated liquidity. And this is going to be of assistance as we move through some of the other concepts of this lecture material, and then also moving into into further research after this. So we're not going to be doing the homework questions. Instead, we're going to be revisiting some of these concepts. So just recall that from the last lecture, what I was trying to demonstrate with some sort of visual proofs is that the way that the Bancor V2 formula operates is to essentially add an amplification factor to the Bancor V1 formula, which means that you end up with a curve that behaves as if it has more liquidity in it than it really does. And in the language of the patent, we refer to this as virtual liquidity or virtual token balances. But that doesn't mean that you can actually trade virtual tokens. It just means that the liquidity pool behaves like it has more tokens than it does, and we refer to that difference between the way that it behaves and how many tokens it actually has as being a virtual balance. So you can't trade those tokens out, which means that you still end up in this position of running out of liquidity at some point. Now, the problem, I think that, with how I presented it, was that when I gave these formulas, and they were on a very large number of slides, I've got this sort of equals C part, which actually just means that this is a constant value. So it didn't mean that these are necessarily the same value. And this is where I want to come back and actually, change the way that these formulas are presented. So the reason why I want to change it is that it isn't apparent necessarily that that C value is under the influence of this coefficient, or it even suggests, I think unhelpfully, that these two numbers might be the same. And so I think to demonstrate how this C constant looks under different situations, let's have a look at a very familiar category of liquidity pool, which is one that just contains two stablecoins, which is going to be of assistance when we look at the stablecoin curves later in this lecture. But let's just imagine that we're adding equal quantities of both of these tokens, so it's a two-token pool, and obviously we have the same reserve ratio for both of these assets. So in the Bancor V1 case, the virtual balance, you could say, is equal to the real balance. Whereas in the Bancor V2 case, because we've applied this amplification constant, in this case 10, the virtual balance of tokens looks to be 10,000 rather than 1,000. And given the formulas, the way that I presented them in the last lecture, you would see that the liquidity constant in the Bancor V1 case is 1,000 and the liquidity constant in the V2 case is 10,000. But because they have the same symbol and because we're referring to the same token balances, this is where I think it's actually a little bit confusing. So instead of using the same symbol for both of these constants, I thought maybe it might be better if we introduce a new constant, capital C, where capital C always refers to the amplified size and little c always refers to the real size. So in this case, you can see that Bancor V1 is just a special case of Bancor V2 in the sense that its amplification coefficient is 1. And in the V2 case here, where we're applying an amplification coefficient of 10, the amplified size is 10,000. But this means that we can actually give both of these pools the little c, the lowercase c constant of 1,000. And this, I think, is going to be, it's going to make the contrast between virtual and real reserve invariance a little bit more precise, or at least it's going to be stated more explicitly. I think, some of the things that I said in the last lecture will become more evident now through the lens of this treatment. So, rather than saying that this amplification coefficient multiplied by the product of all of these virtual balances raised to, all of these real balances raised to their respective weights equaling C, we're going to let it equal capital C. And then it's just a matter of having a look at what is the relationship between capital C and the amplification coefficient. And of course, no mystery, it's just A times whatever little c is. So rather than saying the V2 formula is equal to this constant little c, let's just say that it's equal to A times C. And then from there, I think we're going to be able to derive the V2 formulas in a much more convenient, maybe a little bit more intuitive manner. So we're now going to take this relationship and define V2 in terms of V1 so that we can get to the invariant equation that we've already derived in the last lecture. But this time we're going to derive it a little bit more explicitly in the context of formal logic. So there is going to be some language on these. There are 3 slides of this, and I'm just going to tell you what these things mean because I realize, well, first of all, I may be abusing the notation. This is something that I conceded in lecture 1 that I'm known to do. So I'm just going to explain what I mean with these statements, and I assure you it's a little bit more, it's not as scary as it first looks. So the first thing to realize here is that we're saying that the V1 invariant function, let's just call that capital I, is written like this. So we're saying that I of a bold-faced X is the product of all of these real balances raised to their reserve weights minus some constant value. And that's what, this just means is congruent to this, or it means exactly equal to this. Where this X, this bold-faced X, is not a single point, but is not a single value, but is a list of values in n-dimensional space. And the reserve weights are again exactly what they've meant prior, what we've discussed previously. And so now, once we have this this equation, we can define a predicate, which we're going to call V of X, which is true if and only if I of X is equal to 0. And this will define a set of coordinates that form the bonding curve in 2 dimensions, or the bonding surface in 3 dimensions, and hypersurfaces beyond that. So we say that for the set of all points X that satisfy this predicate is the bonding surface. Then for V2, before we say that what the actual function is, we're going to say first that there is that we're just going to say that it exists and that it has similar properties to the V1 invariant. So where we were using I for the V1 invariant, we're now going to use capital J, and Y here instead of X, but where Y is still a list of coordinates in n-dimensional space. So we're going to use the same predicate, W, that's true if and only if whatever this invariant is, and we don't know what it is yet, is equal to 0 for a set of coordinates that Y represents. And so we can also define a surface or a hypersurface, which is the set of all lists of coordinates Y that are in, the reals in n dimensions where this predicate W happens to be true. So it's not, it's not too complicated. All we're saying is that, whatever we're defining the bonding curve to be, or whatever defining the bonding surface to be, is all of the coordinates where some function, is equal to 0. So, and this is the part that I don't think I nailed in the last lecture. What we are trying to do here is to define how the V1 variant and the V2 variant are related to each other. So we've already said that there are these two surfaces. One surface S is the one that we get from the V1 function, and the other surface T is the one that we're getting from this new V2 function, or functions I and J in the language of the last two slides. Now I'm just going to declare that there is a point that I'm going to call the pivot, which is this lowercase boldface p, and I'm going to say that it is a point that is on both of those surfaces or on both of those curves. So again, this, to read this, this formal logic sentence, this just says that there exists exactly one point in n dimensions such that is a member of both the sets S and T. So there is a set of coordinates that is on both the V1 and the V2 surfaces, meaning that if we take those coordinates and put them into the V1 formula, we will get 0. And if we put it into the V2 formula, we will also get 0. And there is only one list of coordinates that will give us that result. Every other set of coordinates that you feed into both of those functions, you might get 0 in one of them, but you won't get 0 in the other ones. This is a very special, very unique point. And it's going to be the thing that gives us a lot of power, both in defining what the V2 function is, but also in solving other problems down the track that I'm going to show you in just a few slides' time. But this actually isn't enough. What we're also going to say is that at this point, whatever it is, this list of coordinates in n dimensions, that the partial derivative of both functions I and j with respect to any of those dimensions, it doesn't matter which one that you choose, will be equal to each other, and that any point that we're saying, so for any other point which we're calling Q, that is not P, right? So the way to read this is just for all points Q in the reals and n dimensions except for this point P. That's all that thing means. The partial derivative of the function I in any dimension is not equal to the partial derivative of the function j in the same dimension. So long story short, I know that this is a bit of a mouthful. What we're saying is that there is one point that is on both of these curves or is on both of these surfaces. And at that point, the partial derivative or the gradient in any dimension is the same also on both of those curves. So at this one place, like if you were to be on P, right? Imagine shrinking yourself down to to a single point. And if you were standing here, what we're really saying is you would not be able to tell which function you were on, right? It would look the same at this point if you're on the V1 function and the V2 function. And that is what is unique about this point. Any other point on any of these other surfaces, you would know, right? That this is the V1 curve or this is the V2 curve. And using this point, we can actually start to interrogate some of the problems that we were looking at in the last lecture, but I think in a slightly different light. I realized that it's a little bit more cerebral this time. but it's still going to be, I think, a much more direct way to attack the problem that I was trying to, and I think, not doing a great job of in the last lecture. So what I'm going to be doing here is I'm going to be swapping the surfaces S and T just for V1 and V2, just so that we know, at a glance which one we're talking about. So it's just a quick change in the naming convention here, but doesn't really change the meaning of these expressions at all. Okay, so this was the problem that we were trying to solve. And that is that if you don't want to deal with virtual token balances and you do want to deal exclusively with real token balances, this means that we are essentially trying to drive this blue curve down so that so that at the point that it's running out of X tokens, it's now being driven off the origin point. And when it's running out of, when it's Y tokens, it will be again beneath the axis here. So I think it should be at least visually intuitive that, if we've got some point Y0 and X0 here, and we multiply Y0 by some constant and X0 by the same constant, that the gradient at X0, Y0 is going to be the same as it is at A times Y0 and A times X0. And this is something that you are already familiar with, because you know that the standard hyperbola that we have, that has been sort of spread throughout DeFi, the way to get the marginal price is just to take the balance of one of these tokens and divide it by the other. And so if we're taking the partial derivative up here, it doesn't matter what this coefficient is, right? If this is a 1 in the case of the V1 Bancor curve, or if this is an A in the case of the V2 Bancor curve, and whatever this leading term is, it just cancels out. And so it's always just going to be, Y0 over X0 in both cases. So these lines are parallel and they are tangent to their curves at at whatever this pivot point is, where the relationship between these 2 points is just that we have sort of amplified one by this leading A term. So when we pull it back, right, what we're doing is we're choosing this point and we're kind of pushing these two things together. And there's something that we already know about it. So one is that point P is going to be common to both curves because we made it so, right? That transformation that we just did by pulling this curve down from its, its amplified or virtualized token balances down to its real token balances, because the curve begins with X0 and Y0 tokens in it, then this must be the point on both curves that, where if you were sitting there, you wouldn't know which curve you were on. And, to that same point, the gradient we just saw when we drew those parallel lines is also the same there. So this point is the one that we want. It's the thing that is common to both curves and has the same partial derivative in any dimension. And this gives it amazing, not just problem-solving power, but also sort of defining power. You can sort of phrase or frame the amplified curve, the V2 curve, in terms of this point in a surprising number of contexts. And I'm going to show you that in just a minute. So I'm referring here back to pages 40 to 64 of the last lecture. But it's not like, I'm not expecting you to be able to recall everything that we spoke about there. Just know that I did provide a visual proof of some of the things that we're discussing. And so I'm going to skip over some of those details just so that we can sort of get right to the crux of this argument. So this was the formula that we wanted to examine. And after some brief rearrangement here, negating the parentheses and then gathering like terms so that we end up with A-1 as a factor, means that we can get to what I think is a slightly better representation, but this is, all three of these equations are redundant with each other. Okay, so Now, coming back to where we left off, just before we went into some of that formal logic argument, we said that there is this, product of amplified balances is equal to whatever the amplification coefficient is multiplied by the product of just the real balances, and that is equal to capital C. And we've already looked at the fact that capital C is just equal to the amplification coefficient times whatever little c is. So we can very easily substitute out some of this stuff because we have an expression now from the patent itself and from the visual proof that we did in the third lecture, where we know that any of these virtual amplified token balances can be expressed in terms of the amplification coefficient and whatever the real token balance is. So we can get rid of this part in the middle and just say that the product of this thing here, which is the way to calculate the virtual token balance, is equal to A times C. Now this C part, that is this point, right? This bold-faced P, the thing that started or was the point common to both curves. And you can express that as being, C is the product of all of the things within that coordinate system, within that list of points. And so this is the substitution that we do in order to get to the formula that I actually presented you with. And remember, I said that gamma is another one of the terms that we use, which is just the inverse of the amplification coefficient. So this is actually a slightly more, let's say, a slightly more robust way of arriving at this expression, or showing you how to derive it from sort of first principles. And I didn't do it just for the sake of completeness. There are some of these steps that we did, especially the origin point, the pivot point, that we're going to be using in the next part of this lecture. So this is the end of the addendum to lecture 3. Just for context, this means that we're done with the seminal archetype, which was the Bancor V1 formula. We've had a look at nomenclature, conventions, and so on. We went through how that works in any dimension, and now we've basically completed everything that is necessary, I think, in terms of virtual tokens and augmented hyperbolas, or at least in the context of what we call amplified or concentrated liquidity. And so with this lecture, what I wanted to do is to further explore some of these concepts. There were, I think I bit off a little bit more than I could chew in terms of the amount of material that I wanted to cover with part 4. But I did want to build on, I like this idea that we kind of take some of the learnings from the previous discussion and then continue on and kind of keep adding to stuff. And so while I did want to get into things like curve and other things, and we will do that later in this lecture, I wanted to go one step further and have a look at what you might consider to be an exotic bonding curve, which is Uniswap V3. And more importantly, I wanted to show you that actually you already know what the Uniswap V3 invariant function is, because it's the same as the Bancor V2 function. And this is what we're going to do in this part, because I think that while the bonding curve is the same, its expression is certainly unique, right? These two equations look like they don't have very much in common. The Uniswap one has square roots in it, for example. It's got this L term. What is that about? And so I think that there is some value to the algebraic manipulation, or at least a demonstration of the algebraic manipulation of these things into different forms. And there's more than one reason for this. One is that I think that it is helpful to know that if you are implementing a bonding curve in a smart contract, that there are a very large number of redundant ways to express exactly the same idea. And this has consequences on things like computation resources and memory, the number of variables you have to store, and this kind of thing. So I think this process is going to be valuable as a bonding curve research group, so that you guys know that just because there is a formula that someone's published, that there isn't a better version of it or something like that. And I just think that the exercise is also extremely nourishing to the intellect. So let's start. First, you have to realize that with Uniswap, just like Uniswap V1 and V2, Uniswap V3 is limited to a two-dimensional space, which is totally fine. This isn't a limitation or a shortcoming of Uniswap in any way. This is just like a design choice that makes things like not just the smart contracts easier to implement, but also from a product perspective, it makes it easier for users to understand what they're doing. So that step that I did there was just to take just to realize that we've got only two dimensions that we need to handle. And so having this large product operator is not really necessary anymore. And also that we are only dealing with the case where we've got equal reserve weights. And remember, the reserve weights usually have to add up to 1, which means that our x and our y in this case are both going to be 0.5, which is where this square root comes from. So if we get rid of that square root by squaring both sides, we end up with an expression like this. No, I'm not going to do the tedium here of rearranging this equation to get it in terms of y. This is something that I'll let you do on your own, but relatively straightforward to do that. Some of the other expressions that we're going to go over in the next couple of slides, actually, I'm going to show you how it's rearranged. And similarly, I'm not going to show you how to differentiate this, but just take my word for it right now that this is the differential. I am also, I want you to note here that in general, there's kind of this implicit convention in DeFi that we always represent that we report the gradient positive all the time. And this means that whenever you take the first derivative of one of these curves, you have to move the negative sign to the other side. So we're always talking about an exchange rate, or usually we're talking about an exchange rate. And so people don't really think of something as having like a negative value. So to say that the swap rate of USDC to USDT on curve is -1. Is actually true from a calculus perspective. But in a financial perspective, we think of it as being 1-to-1, like it's a positive number. So just know that I will observe that convention throughout the rest of this lecture and through most of the material that I write. Okay, so first time that our friend P is showing up again. So remember, this x0, y0 coordinate was the thing that we said is common to both curves, right? This expression here. And so every time this thing pops up, if we wanted to, for the sake of clarity of presentation or something else, we can always feel free to replace this with the letter C, which remember is actually referring to whatever the hyperbolic constant would be, K, if this was an unamplified curve. Right, so in the familiar xy equals k, that k value is equal to this c value, and so it does tell you something about the actual number of real tokens that there are underpinning this thing. Now, the other thing that you'll notice here is that the form that this partial differential takes is or it should appear quite familiar. In the case that we were dealing with, let's say, an amplification coefficient of 1, right? Then this would, this part down here would cancel, so it would end up with 1 minus 1, so this becomes 0 and cancels out this x0 term, and we would end up with just x squared. So 1 over x squared times c is the familiar, marginal price equation, or one of the familiar marginal price equations from like Uniswap V2 and Uniswap V1. So to have it sort of presented this way, I find at least a little bit, it's kind of deeply satisfying in the sense that even though we're kind of in this exotic, amplified liquidity space, the same sorts of equations continue popping up, and it's just deeply satisfying to me to see this kind of thing. Okay, so how to use this. What we're going to do is we're going to be examining this x dimension here. So we're always quoting we're always using an x coordinate here to determine the gradient. So if we have a list of possible x values to use, then this means that we can actually decide which points on this curve might be of interest to us. So we know that I'm sorry, this is the marginal price, right? So if we have a look at where I've drawn this dashed line, you can see that it comes up from some x value, it touches the curve at some point, and then at a right angle to that point is where we would have some corresponding y balance of tokens in the real sense, right? These are both real token balances. And the tangent to the curve at that point is the marginal price. So how do we start? We're going to say that when x is equal to 0, right, at the point where we have some maximum amount of y tokens and all of our x tokens have been depleted, this is this is a significant point for us because it is the marginal price at the bound of our amplified liquidity curve, right? At the point where it's crossing the y-axis. And so I choose to call that point, or the gradient at that point, I should say, PA. I think you'll find in the Uniswap documentation, they call this point PB and the other one PA, but it doesn't matter, right? They're just symbols. I just like the idea of like reading left to right or even top down. So I feel like A should come before B in this case. But yeah, just remember that PA is the steeper gradient. It's the one that's leftmost, right? It's the one that is at the y-intercept when we've got no x tokens left. Okay, what about the next point? Well, if we're getting the gradient of this curve, right? The gradient of the tangent line at the point where the curve is leaving the is cutting the y-axis, then it would probably be good to also get the gradient at the point where it's cutting the x-axis. The problem here is that we can't just give it x is equal to 0 here, or we can't give it, y is necessarily equal to 0 in the straightforward sense because we don't have the partial differential expressed in terms of that. Now we could go back and and just define the derivative in terms of x over y, but I'm going to show you something that I think is a little bit more interesting, which is if we go back to the invariant function that we have in terms of y and set y equal to 0, then necessarily whatever the x coordinate here is going to be that x-intercept. So if we rearrange the equation to get rid of all of the stuff that we're just going to be either multiplying by 0 or dividing into 0, we end up with this expression. Which means that we can rearrange to get something that is relatively compact. And you'll notice that this is also a constant. So if you have, at the time that you determine what your bonding curve is going to be, right, when you're giving it these parameters, whatever the x0 coordinate is in the amplification coefficient, you already know what the x-intercept is, meaning you know that if you run out of y liquidity, what the x liquidity is going to be left inside this curve. And so if we plug that point into this equation, then we're going to get another derivative. This time we're going to call this one PB. So PB is the more shallow of the two, meaning that by definition, PA is going to be a larger number than PB. And this is, again, I think a more intuitive way to think about things. Okay, So plugging PA and PB into the into these formulas, we end up with these expressions. Here on the top row, all I've done is to take this C term back out, because remember, it's just x0 times y0, which means that we can get rid of part of this x squared, which is helpful because now we've got the same quotient here of y0 by x0, which is going to be significant in just a few moments. So what I've done here now is to basically isolate the square root of PA and the square root of PB. If you didn't see that, that transformation, let me go back. It's not too difficult. You can see that we've got a squared and a minus 1 squared in both of these expressions. And we already kind of have this light at the end of the tunnel with respect to the Uniswap formula that we're trying to derive. And so we're kind of already expecting that we're going to be taking the square root of PA and PB at some stage. And in a way, this expression here is also kind of pushing us in that direction, just because we've already got both the numerator and the denominator squared as a result of the algebraic manipulations that we've already completed. So when you're kind of doing these things, just know that square roots of things kind of tend to pop up all the time. You shouldn't be afraid of them or feel like you're sort of, meandering down some, some useless factorization method or something, because it turns out that these square roots are just a very natural component of hyperbolas in their algebraic expression. So rearranging these equations by taking the square root of both sides gives us these these depictions, and then rearranging these to isolate a minus 1 gives us these expressions. Now you might think that's a really weird thing to do, right? If you were to sort of just blindly be thinking about about how to get a better, more intuitive, invariant function or something, isolating a minus 1 seems like a weird choice until you realize that the equation that we started with just a few slides ago has this a minus 1 factor already inside it, and that that factor is being multiplied by the two components of that coordinate that we're defining the point that is common to both curves, right? Both the V1 and the V2 curve. So this x0 and y0 term is kind of the thing that we're trying to cancel out, right? Or that we're trying to get a better perspective on. So we know that these A1 terms are the things that we're going to be sort of moving into this expression that we're going to be substituting out. And then the question is, like, which one is going to go where? Because you will note here that while both of these things are, have A1 on the left-hand side, the right-hand side is not the same, which is, intriguing. So we've got two different definitions for the same algebraic identity. And, there are a bunch of things that you could do from here if you really wanted to. For example, you could set the right-hand side of this equation equal to the right-hand side of this equation and get some other really interesting properties out. For example, what does y0 equal in the context of just these other things, right? If you've got a marginal rate or the square root of the marginal rate at the point where the curve is cutting the y and the x-axis, can that tell you something about, the other coordinate, x0? Or if you have x0 and y0, what do you know about the marginal rates at the intercepts and so forth? But yeah, so here we just need to decide, even though these things aren't the same, which order we're going to substitute them in, right? Which one goes where and why. And the thing to look at here, and again, just a sort of a word of advice, if you're going to be exploring some of these things or some of these concepts on your own, again, don't be afraid of things coming out in square roots. So when you see, when you have an opportunity to divide some number by its own square root, remember that you are always going to get the square root of that number back, right? 2 divided by the square root of 2 is always the square root of 2. And that can be helpful because now you're kind of going from like two different variables to the same variable. Like it kind of gives you this really nice sort of simplification where you end up, where you start off with twice as many terms, and then after doing this kind of after doing these steps, you can end up with fewer terms than what you started with. So substituting these A-1 terms using the definitions that we derive from the marginal price equations above, we end up with these expressions. And again, you should be able to very quickly identify that we've got this P term showing up again, which is the point that is common to both the V1 and the V2 surfaces. Again, just for the sake of repetition, recall that this C term is the hyperbolic constant. And if we wanted to, we can substitute out these x0, y0s just for square root of C in this case. And now we've actually got something that looks pretty familiar. This actually is the Uniswap V3 invariant function. It's just that instead of expressing, instead of expressing it in terms of the amplification coefficient and, this point that's shared on both curves, or the hyperbolic constant that for the unamplified curve, Uniswap has taken these two things together and created this new term that they call L, right? So just, I think that even by itself, this is a helpful thing to know about the Uniswap bonding curve, is that L component, like if you read it off of the smart contract, it's actually telling you about some amount of amplification that has been, done to some other bonding curve, right? Some smaller bonding curve. So all of the same intuitions that you've had leading up to this point also apply to Uniswap V3. It's only in 2 dimensions, and it's only for equal reserve weights. One of the things that is a bit odd is that if you try to use something like the Uniswap invariant to define things like a swap equation, you end up with some very difficult cumbersome equations. Whereas the ones that I've shown you for Bancor V2 were relatively compact. The Uniswap V3 ones are enormous. Now, the reality is that it doesn't matter because both the smart contracts in Bancor V2 and the smart contracts in Uniswap V3 both just use the virtual token balances, because it's much easier to just apply that amplification and then pretend that you're on a normal constant product bonding curve and just use the same swap equations that you had there. So it's only under very special situations that you would even want to deal specifically with token balances, because if through this programming hack you can end up in a situation that's much easier to solve than you using sort of less computer resources to solve a swap equation, then you should always be taking that out, right? You don't always get such an elegant way to solve a problem. So even though these are the implicit solutions to or the implicit swap equations to Uniswap's published invariant, just know that when you actually do it on the smart contract, I think they just use the virtual token balances anyway. So these equations aren't even used. We're only going through it now just to look at what the consequences are of defining your invariant a certain way, and that even if you end up with something that is relatively beautiful, and I think that the invariant that Uniswap uses is pretty attractive, it's not always the case that you end up with with as elegant or as concise equations when it comes to producing things like the swaps or the liquidity provision or other applications that you might have for it. So it's the end of the Uniswap V3 component to this lecture. And I thought that this would be a good opportunity to introduce you guys to Carbon, only because it is using a very similar sort of theoretical basis to Uniswap V3 and Bancor V2. So recall that one of the ways that you can think about amplified liquidity is that there is, some smaller bonding curve that you are emulating, and you're just, you're drawing a little box around some section of that curve, and you're trading on a much larger curve instead. And we can define that either by the the coordinates in the middle of this curve, so x0 and y0, or we can define it at the marginal rate as the curve is leaving the box. So when it's cutting the y-axis, when it's cutting the x-axis. Now, these amplified curves, they behave exactly the same as unamplified curves in the sense that there is one curve to describe all swaps. So if you are on this amplified curve, for example, and you are trading, delta X tokens into it and extracting, delta Y tokens from it, you will do that. You will move the price, and then if someone is let's say less optimistic than you, that the tokens that you brought out of this curve are worth what you paid, they could reverse your transaction in the sense that they can then put the tokens that you took out back into the curve, and then take out the tokens that you put in. And this is that reversible nature. This is the thing that makes AMMs sort of good at what they do, because the market can kind of push and pull on the marginal rates, and that is the sort of mechanism by which AMMs equilibrate to whatever we think that the quote unquote market price actually is. But did it have to be that way? And is this something that users even want, right? When Bancor V1 was designed, it wasn't really, the user, right, the person that is providing liquidity to the curve in the first place, they did want it because they were the project, right? They were the creator of the token, the people that wanted it to equilibrate with the market in a natural way and facilitate price discovery as efficiently as possible. But this idea of a community liquidity provider or a selfishly motivated liquidity provider is kind of incompatible with this idea. Because this act of constantly rebalancing the pool and always being the de facto counterpart in every trade that the market wants to take with you, it does have negative financial ramifications. It's not, despite the marketing and hype and things, adding liquidity to an AMM is generally not a very good financial decision. And if someone is going to provide liquidity, they would probably prefer to decide how and at what price points that liquidity is used. And we know this, like, I don't think that this is a strong assertion, because day traders do it all the time when they create what we refer to as a limit order, meaning that they will add some asset to an order book and say, this will be available to the market when they have an appetite to take it from me at the price that I choose. And when the market takes it from them, they don't expect that if the market changes its mind, that they are going to be obligated to give the market a refund, which is the case on an AMM, right? If this reversibility is essentially, you made a trade as the liquidity provider and the market took tokens from you at a price that maybe you wanted. But then if the market changes its mind, you are then forced to basically give the tokens back in return for the tokens that they took from you. Day traders wouldn't want that. Essentially any trader wouldn't want that. This is an unusual thing to require normal people to accept when they are participating in financial systems. And so the solution maybe is to think about what it would mean to have two different bonding curves that define trades only in one direction. So that the positive delta x minus delta y curve is distinct from the negative delta x positive delta y curve. What do I mean by this? On the, let's say on this blue curve, we've got, I don't know, let's say in ETH on the, this might be an ETH USDC curve, for example. And so someone can be pushing one of these assets in, let's say, it doesn't really matter which one it is, but let's say that they are able to put one of these tokens in exchange for the other. But if they wanted to change their mind here and put the tokens back in, they would have to do it on the other curve, right? So they can't reverse this transaction, and or no one else would be able to reverse this transaction for them. The person who is creating these curves is literally dictating, mandating that one of these curves is for trading in one direction and the other curve is for trading in the other direction only. What would it look like? I'm going to pause this for a second. So this is a part of a software suite that I've created that is for modeling AMMs, at least in a financial sense. But there are a couple of heuristics here that I think that you'll find useful. So what I'm going to do here is I'm going to compare Uniswap V2, Uniswap V3, and Carbon. And the reason we're going to be doing this is, at least in the context of our discussion, is looking at how you can think about a bonding curve from a completely different perspective. So here you'll see that what I have is a depth chart. This depth chart which is represented at the bottom left of my screen is what you would get if you were to look at what we've got the price chart up here. If you were to take a vertical slice of the price chart and sort of look at it from the side on. So at the current market price, whatever the price of this actually is, this is an ETH BTC simulation. What you can see is that there's always zero liquidity at the current price, and this is generally true. And then as we move in one direction on the constant product system, you can see that the liquidity is constantly increasing. And this is true in the other direction as well. Now, both from, the first lecture, but also from, your guys' general knowledge of DeFi, that a constant product AMM never runs out of liquidity. So these, this depth chart does, run off into the horizon, but at a square root profile. So it still has a finite amount of liquidity. It's just spread over an infinite surface area. So let's run this this animation and see what it does. So first thing you'll note is that as the price is moving around, you'll see it will kind of push on the boundary of this depth chart. And as it does, it's always converting one of these assets into the other asset. Again, you know this. So when the price is moving up, it's taking our risk asset and converting it into cash and putting that cash immediately behind the current market price. So you can see every time this white line moves into our red liquidity, the green curve sort of moves up to meet it immediately. And in a sense, this is what market makers are supposed to do, right? If you are an exchange or if you are a token project and you are trying to make sure that there is a market for the thing that you're offering, then when you are having a conversation with your market maker, one of the things that you are discussing is basically what this liquidity depth profile is going to look like. And market makers also need to, understand the financial risks that they are taking on by providing liquidity of a certain profile. And so their appetite for risk and how strong their incentives are to participate will determine sort of how healthy that liquidity book looks. And so in general, a healthy, a very liquid system, something like cash, so something like USDC into euros, for example, will have an extremely deep depth chart that would require catastrophic changes in price in order to really move it would require catastrophic changes in the market to move the price significantly. Basically, there's so much liquidity around the current market price that it's very, very difficult for anyone to move it. Whereas typically things like Bitcoin and Ethereum and so on, the books are a lot thinner, and so market movements can have much more catastrophic effects on the price. Now, there's a couple of other things I'm tracking here, and I think for the purpose of these talks, we don't necessarily need to pay attention to them, but just know that the simulation does keep track of the financial performance of this portfolio and its fee denomination and so on. But I think for our purposes, in the context of these lectures, we really just want to pay attention to the price chart and the liquidity depth chart so that we can get an idea of how these different bonding curves respond to different conditions. This is the same simulation, but instead of having the depth chart and the fee chart, I'm now looking actually at the bonding curve itself. So as the price is moving up and down, you can see what's happening is I'm now using a crosshair to track exactly where we are on the constant product bonding curve. And I've presented it deliberately in two different ways. So one is the transpose of the other, meaning that if I've got the ETH balance on the y-axis and the BTC balance on the x-axis in the bottom left, then I'm just flipping those in the bottom right. So the BTC balance on the y and the ETH balance on the x. This is going to become a little bit more obvious in a few slides' time as to why this is on here, because I realized that it seems stupidly redundant to do it. But just realize that when we are watching these market movements occur, that any change that we're seeing in one of these charts in the bottom left has some sort of reciprocal motion in the chart on the right, at least on Uniswap V2 and Uniswap V3, meaning that essentially these are the same chart. I think is the best way to say it. The purchase or sale of one token on one of these charts is the same as looking at it from the transpose perspective on the other chart. Doesn't really matter which one of these graphs you're on, you already have enough information on one of these to construct the other. Let's have a look at Uniswap V3. So the first thing you'll note, and I'll pause this, oops. The first thing you should note, here we are. So the first thing you should note here is that we are no longer enumerating the liquidity from a zero price point to an infinite price point like we were on the typical constant product. So remember, just a handful of slides ago, we actually showed that when the real X token balance is zero, we can measure a marginal rate, right? When we've run out of that liquidity. And then by setting, the X to its X intercept, we were able to measure the marginal rate as the Y token is running out of liquidity. And so that's what we've effectively got here. The bottom of this range, of this green range, is, let's call that P, that'll be P, PA or PB, depending on which one of these assets you're using as numeraire. And then the other one would be, PA or PB, whichever the opposite is. And what you will also see, and this is something that I really wanted to address in these lectures, but we never actually got to, is that there is this gap between the green band and the red band. And this is because of the fee, you're effectively looking at, there's a part of the bonding curve that's effectively removed. And so there's a discontinuity between the marginal rates, but that's again something else we might be able to explore in a lecture in the future. Long story short, there is now a limited range of marginal rates that we are going to be executing over. But everything else is pretty much the same. And I'm just realizing now that this is actually the, let's do the depth chart one first. So same simulation, same price chart. So as it moves around, it's doing exactly the same things that it did in the Uniswap V2 case. Every time the price moves up, we are going to be consuming some of our risk liquidity, in this case, Bitcoin, and converting it into ETH. And the ETH appears again beneath the current market price. And when this chart eventually turns around, you're going to see that as it moves through our cash liquidity, which in this case is ETH, it is converted into Bitcoin, and that Bitcoin appears immediately behind whatever the current market rate is. So this is that example right now. So let's pause it right there, where I said that if you're in a concentrated liquidity system, and Uniswap V3 is a concentrated liquidity system, it's possible to completely run out of liquidity. So here, as long as the price of Bitcoin is all the way up above our range, we only have ETH tokens. So this is, the case where, either we're at the X-intercept or we're at the Y-intercept, and we're still quoting a marginal price at whatever this bound to be. But in fact, the market rate is something else entirely. So when we have when we have only one token left, we actually lose the ability to quote an accurate market price anymore. And this is one of the trade-offs of having a concentrated liquidity system. But the competition for trading volume means that there's generally liquidity at all price points on something like Uniswap V3. And even if retail users aren't doing it, Uniswap and their partners seem to be capable of bringing liquidity into the system to maintain it over long periods of time anyway. Okay, so that's the depth chart component. You'll see that this is a little bit more chaotic as well. But this is, again, just because we're zoomed up on such a small part of the bonding curve, that small changes in the price have a much more dramatic effect in terms of price. Okay, so the invariant function looks, again, pretty similar to what it looked like for Uniswap V2. So these aren't triangles. This actually is, this does have a very slight curve to it. And again, the marginal price at the end here is whatever the marginal price on the price chart says it is. So you can see here that the bottom of my green range is at about 13 point something, and so the marginal rate of the curve as it's leaving, as it's becoming depleted of one asset, is also going to be 13. And the reciprocal will be true in the other for the other asset. But again, these are the transpose of each other, and so whenever one of these triangles is responding, the other one is doing the same thing, but from the opposite perspective. So if I wait for the price to come back in, here we are. You can see that on the left, where we've got the ETH balance on the y-axis and the BTC balance on the x-axis, the small red triangle here is a graphical representation of the amount of liquidity, or the depth of liquidity that we have left in Bitcoin. And if you have a look at the price chart, you can see just visually that's easy to confirm, right? Because the price of BTC is currently moving up through that range. And so the difference between where the current market price is and the edge of our liquidity bound is relatively small for Bitcoin and relatively high for Ethereum. And so we would expect that the amount of ETH liquidity that we have to be comparably large compared to the amount of Bitcoin liquidity that we've got left. And that's true on both of these charts. And again, this is just a redundant way, maybe overly repetitive, of showing you that these two charts are there is a symmetry here. They are effectively the same chart. And this is a key takeaway because carbon isn't. So this is, remember, the two different bonding curves that I said we're using to change the way that things trade. So first thing to note here, and I've paused it, is that as the price of Bitcoin is coming down through this range, we're getting, we're depleting our ETH liquidity. And again, nothing too shocking there. This is, I guess, a property that, Carbon shares with something like Uniswap V3, for example. But the bids are not coming down to meet the market price. So for the first time, we're seeing this kind of gray region start to appear that wasn't present in either of the other simulations. And this will be, this will be maintained. So you can see on the depth chart, we've basically almost completely run out of Ethereum, and our Bitcoin wedge is now quite large. And here, as the price of Bitcoin went up, we're now trading on the other bonding curve, right? So the market then has an appetite to take BTC from us at a completely different price point. And so we gave it to them. And when that BTC was sold for ETH, rather than the ETH coming back into the same bonding curve that we were selling BTC on, that ETH is now going to the other bonding curve that we were selling ETH on. And this is the thing that makes Carbon's bonding curve so special, is that they aren't n-dimensional, they are one-dimensional. They only have their own token on them. And this means that you can compose them together, as many times as you want, to create, an n-dimensional bonding curve if you want one. So here, for example, we've obviously created from two bonding curves a two-dimensional system, but one that lets us choose the marginal rates that we trade at independently of each other's balances. One of the ways that I've just described this, for example, when I was in ECC, is that up until the advent of Carbon, all of the bonding curves that we use throughout DeFi are explicitly using the balance of another token to quote the price of a token other than that one. For example, if you've got an ETH USDC curve, you kind of use the balance of USDC to quote the price of ETH, or use the balance of ETH to quote the price of USDC, and so on. With Carbon, you don't do that. You use the balance of ETH to quote the price of ETH, and you use the balance of USDC to quote the price of USDC only. They don't even know about each other's balances, which is pretty interesting. On the invariant side, again, you will see, oops, gotta stop hitting spacebar. You'll see on the invariant side, again, straight away, that these things are starting to look a bit different to what we're used to. So for the first time, at least in the three simulations that I've shown you, we now have an example where what's happening in the bottom left of this presentation is different to what's happening in the bottom right. And so as I let that play out, you can see that, again, this is just a different graphical representation of what we're seeing on the price chart. But essentially, there is no BTC balance in the ETH pool, and there is no ETH balance in the BTC pool. There is only one token in each. So this big gray, chasm that's appearing for ETH is it's representing a void, right? That we used to in the old paradigm just let be populated by the other token of the pair. But what we're saying in Carbon is just let it be unpopulated. You don't need to have another dimension there. It's okay to have a one-dimensional curve, which I know it sounds counterintuitive. Like, how do you even visualize a one-dimensional curve? And you'll see, I've actually labeled the x-axis in both of these plots, the fictional x coordinate, and it is because to have a bonding curve at all in the traditional sense, in Carbon's context, requires you to perform an integration, which means that you kind of get back a dimension that wasn't there before. So the x-axis in both of these animations is just the shadow of that integration. It's not a token balance. And this is the first example in DeFi of a bonding curve being constructed this way. So other than that, I think, once you've wrapped your head around that concept, the rest of what you're seeing here should make more sense. But yeah, this is a dramatically different way of thinking about concentrated liquidity and the way that it can be used to create different things. Obviously, as a DeFi product, our focus is always on trying to either support projects and their liquidity needs, or in the case of Carbon, support people that are wanting to engage in financial markets for selfish reasons. And so Carbon is really the product for them, for the latter case, whereas Bancor V1 and even Bancor V2 to some extent was mostly for the former case, right, for supporting projects. Just quickly, you can have a look at, there's like a Bloomberg sort of style way that we can sort of capture the differences in the way that these different bonding curves behave. And this is, again, just having a look at that same simulation. And what we're, the thing that you ought to be paying attention to here is the difference between the blue and the yellow curves. So the blue line here, the blue trace, is the portfolio valuation, meaning the LP position inside this, inside these systems. Whenever it is above the yellow line, then we say that this is in a state of impermanent gain. And whenever the blue line is below the yellow line, we say it's in a state of impermanent loss. So Uniswap V2 over this particular simulation, I didn't do too bad. I think it's about a 1%, 1% gain. Uniswap V3 is kind of showing us what it's made of, because it did perform much better. But if you were paying attention during the animation, you would have noted that it's not without risk. I think the biggest capitulation that we saw in the Uniswap V2 case was, I think, negative 4%. It might not have even have been that high. I think it might have even been negative 1.4%. I can't remember now. Whereas for Uniswap V3, it was something like 15% capitulation, which is much more aggressive. But at the same time, after the price of Bitcoin came back into range, the profits that you get from a concentrated system can be significantly higher than the unconcentrated one. I think it's something like a 15% return as opposed to 1.4 or something like that. But Carbon, because of the ability of it to hold on to value for longer, right? Wait for better prices, both when you're buying something, so refusing to exchange your cash for the risk asset until it's an attractive price. And similarly on the upside, refusing to exchange your risk asset back to cash until it's valuable enough, means that it accrues value actually in a much more dramatic way. And this shouldn't be too surprising because it's no longer, strictly speaking, sort of a short gamma protocol, but it's something that's much more akin to sort of alpha generation, or much more aligned with alpha generation. We tend to throw around terms like buy low, sell high, and that type of thing, but I think it's a little bit lame, I think, in some situations. The better way to think of it is just that you are, rather than chasing the market for volume, you're instead deciding your price targets and waiting for the market to come to you. So it's a slightly different way to think about bonding curves, and I think for the first time in a DeFi context, no longer using them for market making, right? Carbon is not an AMM. It is a trading protocol. So it will become illiquid. It does become illiquid fairly frequently. The same way that a lot of markets will become illiquid if you only allow people who want to interact with them. So yeah, the summary. There are some things that I wanted to show you. If you want to get further into the weeds, and I do recommend that you do, if you come to our website, right at the bottom under resources, you'll see that we've got the light paper, white paper, GitHub, a simulator repo, which is not the one that I showed you today, but one that is similar. The white paper was authored by myself and Stefan Loesch, and I think if I can move this, here we are. And it's I think it's of a pretty good caliber. The light paper is mostly meant for sort of like marketing purposes, like threaders and things on Twitter. It has the advantage of being a lot shorter, but it's not nearly as in depth. But one of the things that I wanted to show to you guys, and something that I don't show to everyone, and again, this is the where is it? Should be here. Maybe we removed it. All right, I will. I'll just send this to Rabbit so that he can give it to you guys. It used to be up on our website. I'll have to find out where it is. But this is our invention disclosure. So this is basically what I sent to the patent office prior to publishing Carbon. So, you know, Bancor tends to collect intellectual property. And so we've basically had our provisional awarded in October of last year, and we've recently filed for the PTC. But this has an enormous amount of work in it that I think that you will find of interest. So, for example, these are various ways that you can list the invariant function for a concentrated curve in 2 dimensions only with equal weights. So you saw already that there was, like, you know, the Bancor V3 formula, which was essentially this one here, where n is substituting for gamma. And then I showed you that we can turn that into the Uniswap V3 formula. And here are like a dozen other, you know, invariant functions that you might use. Some even using constants that you haven't seen before, things like Q. And what's more special is that some of the, you know, some of the equations that I've deduced here, let's move to the swap equation. So, for example, some of these swap equations, they only reference one coordinate system. So in general, you know, if I zoom back up, in the typical case, so if we were, you know, performing a swap on something like Uniswap V2, you would probably be used to seeing yeah, something like this swap equation, either in terms of k or in terms of x and y. But the point is that it would have both of these coordinates in it. Whereas the swap equations that I've provided in this invention disclosure, again, referencing the one-dimensionality of Carbon's curves, will only refer to one of the token balances. So here, for example, if this was an amount of ETH that's being extracted from a curve for an amount of USDC that is put into it, you'll note that all of this input space only has the X coordinate in it. There is no reference to a Y coordinate. And that's true all the way down here. And if you integrate these things, you can kind of get back to a Y coordinate if you wanted one, but the value comes from not having one at all. There are also some of the, you know, a lot of the geometric intuition has kind of been, you know, very thoroughly fleshed out in this document. And so I think that it's a really good place to start. And the other thing that it has is a bunch of identities. So let me just have a look. Here we are. So in some of the homework that I've given you previously, I've noted that, you know, we might want to, you know, can you define the intercept in terms of x0 and y0? Or can you define the, you know, the asymptote in terms of the marginal price equation or something like that? And so here I've got like a very long list of these identities that actually show you how to convert between all of these different aspects of a concentrated liquidity curve. And some of them are pretty surprising. So for example, I don't know, like this, the y0 coordinate can be expressed in terms of, you know, PA, excuse me, the hyperbolic constant and the the amplification coefficient, for example. So yeah, I think if you really wanted to get really deep into concentrated liquidity expressions, the invention disclosure is absolutely the best place to, I think, is one of the best resources available for doing that. Okay. Okay, that's the end of carbon, but not of the lecture. As promised, I do want to go over the stablecoin curves, and I have prepared a bunch of different Desmos graphical, graphing calculator exercises that we can go through them, or demonstrations, I should say. But unfortunately, because of I had to spend so much time preparing in meetings and things in Europe. I wasn't able to commit as much time as I wanted to developing out these slides. So it's basically going to be this slide plus the Desmos demonstrations and whatever I say about them off the cuff. But these are the two expressions that I wanted to show you. One of them is well known, which is the curve V1. This is I've modified it a little bit from the way that it appeared in its first white paper by Michael Egorov, but it's known. The solidly one that I'm providing here, you actually would not have seen before because it doesn't exist anywhere, not even in the solidly documents. We'll look at the exact instance that Andre Cronje used of this formula. And I speculate that he probably does have the general formula himself somewhere, but he's never shared it with anyone. And so I'm going to share it with you so we can investigate some of its properties, and then we will have a look at we will speculate together on why he went with exactly the form of it that he did. So just know that this expression is, I don't know if it's a secret or something, or it's just something that, no one thought to share with anyone. But this is this is a rare site. You can't find it on the internet or anything like that. Now, there's a couple of terms here that we need to discuss. The first one is this letter D. So the curve white paper does a very good job of defining it, and it's quite distinct from the hyperbolic constant like K or C in the case of the lectures that I've given you. D is defined as being the total number of tokens that exist in a liquidity pool when they all have the same marginal rate with respect to each other. So imagine on like a USDC USDT pool at exactly the point where USDC and USDT have a one-to-one exchange rate, exactly one-to-one exchange rate. So for example, if you put 100 USDC and 100 USDT into a liquidity pool, into a standard constant product liquidity pool, we know that K, in the case of Uniswap V1 and Uniswap V2, would be 100 times 100, so 10,000. But D would be 200, right? It would be the sum of the tokens in that pool. And D has the same meaning in the solidly formula. But again, the way that it is expressed in its own documentation and certainly in its smart contracts, it uses a different variable, but just know that it doesn't really matter. You can convert between the hyperbolic and the constant sum constants without too much issue. Okay, so let's go to Desmos. First one we're going to look at is the curve, the curve version. You guys can just confirm for me that you can see my graphing calculator up in front of you?
Yeah, we can see it.
Perfect. Okay, so you can see here I've just this is the way that it appears in the curve white paper, and I've got a couple of different variables here that we can play with. So D in this case, when we move it around, it's going to have the same effect of changing the K value of a hyperbola. So it basically just moves it in and out of the origin, or like moves it closer towards the origin at low D values and farther from the origin at higher D values. But this A term is the thing that's really interesting. So you can see when we move it around, we get this really spectacular sort of shape developing. And the way to think about it is exactly the same as the context that I raised it in Bancor V2, is that it is like the amplification coefficient. The difference is that in Bancor V2, when A is 1, it's equal to the constant product case. But in Curve's case, it has to be equal to 0. And as we move up, you'll see that it takes on this strange kind of squashed shape. So when we start at 0, it's this beautiful conic section, and then as A increases, it like flattens out towards the middle, but maintains this this asymptotic approach to both the y-axis and the x-axis on either side. Okay, so how do we, is there, maybe there's another way that we can sort of have a look at that transformation. The first one is to have a look at where the constant sum curve is. So x plus y is equal to d. So again, I can show you that as we move d around, we're also going to be moving that constant sum line around. And as we squash this thing down, you can see it really is getting closer and closer to this line. And if I set A to have a higher tolerance, maybe up at 100, you can see that as I drive it farther and farther to the edge, that it actually does start to look more and more like a straight line in the middle. And we have to really get all the way down here to even see that it's that there's any it's tapering off at all, right? At this scale, it really does look like it's just a completely straight line. And this is advantageous for a couple of reasons. The thing that makes Curve such a successful protocol is that it actually solves, and this is rare in DeFi, it actually solves a problem that people were having, which is that stablecoin liquidity is only valuable if you're able to exchange something like USDC for USDT at an approximate 1-to-1 rate, and in very large amounts. And the reason is simple, is that we expect USDC and USDT to be worth about the same, all the time. When you're trying to trade on a hyperbola, though, you actually can't trade anything without moving the price quite significantly. And so this ability to flatten it out and have a much more gentle change in the gradient, so essentially a much more gentle second derivative, means that you can use very, very large amounts of of the liquidity that you have before you start to see a change in its price. And this is, I think, a really, it is a really great idea. This is one of the DeFi protocols that I think deserves our respect. It was not only is the mathematics, but that sits behind this thing, it's unique, right? This is in no way, this doesn't have anything to do with Bancor at all, right? It's not Bancor V1, it's not Bancor V2, it's completely novel. And that's rare. And I think that, like I said, it deserves our respect. But it does have problems. One of them is that you'll see that there's no obvious way that we can change, for example, the incline, right? So it could be that we want something that has a relatively stable rate of exchange, but not 1-to-1. Of course, for USDC and USDT and things like that, of course, it's going to be 1-to-1 forever. But you can imagine some other application, maybe a non-financial application, where you would want the exchange rate to remain relatively stable at some other rate, maybe 2 or 3 or pi or whatever you want it to be. No immediately obvious way to achieve that with this function. The other one is that the swap equations are notoriously difficult to solve. And I'm actually working on, I'm actually completing some work now on how to arbitrage curve with arbitrary precision. And so maybe later on I'll share with you guys some of the swap equations and other things, but I haven't completed that work yet, so it seems premature. But just know that the equations to solve for the swap and things are not very trivial. And to implement them in a smart contract is also extremely challenging. And again, testament to Ergorov's intelligence. He's implemented, I think, a fairly fast Newton-Raphson method that doesn't solve the swap symbolically, but rather approaches, the right output after, I think, 4 or 5 iterations. The curve contracts actually run it a very large number of times, like 32 or 64 or something, I can't remember. I think for the sake of security. But realistically, I think that they almost always end up solved after like 3 or 4. Okay, so the only other thing that we need to look at here is the n parameter, which always refers to the number of tokens or the number of different token types. So it's the same n that you've seen in like our big operator nomenclature. So if there's only 2 tokens in the pool, like USDT and USDC, then n is equal to 2. If there's 3, for example, if you add DAI to it to form the tripool, then n would be 3 and so on. And now we can't, I don't know if Desmos will actually let me graph in 3 dimensions, but it's worth just looking at what happens when we move this thing around. Because it might not be, it could be that this isn't what you expected. And I'm not necessarily sure what I would have expected, but I can confirm that if you go ahead and add other dimensions to this thing, it's really, really important to correctly adjust for this n parameter, or when you start moving the amplification around, you will actually lose adherence to this kind of one-to-one point. If you like, the x0, y0 point on the curve equation. So that's curve V1. So is it brilliant? Yes, right? Did it actually solve a problem that the industry was having? Absolutely. And is it general? Yeah, you can put any number of dimensions into this thing, and it will have this property, in all of those dimensions. So it's really very, very nice. What are the problems? It's not a trivial function to solve for swaps, and it lacks the flexibility to give us a slope of anything other than -1, I think. It could be if we ask Michael, he might say, yeah, look, there's a way that you can, add a new parameter into here and get it to slope a different direction, but I have been unsuccessful myself in realizing that in a, let's say a pragmatic sense, right? And something that you could actually implement on a smart contract. Okay, let's have a look at solidly. So solidly is sort of similar in that it's more similar to Bancor V2, I think, in the sense that when you use its version of the amplification coefficient, which in this case is R, and you can see here it's these things, it's what X and Y are raised to, and when I take this whole thing, I also have to take the root at R plus 1. But when it's equal to 1, you get, again, just the normal hyperbola. So let's have a look at what happens when we move R down to numbers less than 1. You will see that it looks to be doing something very, very similar to curve, right? It gets flatter towards this middle section. And in fact, when R is equal to 0, it becomes a completely straight line, which is something that only happens in the curve equation when you allow A to become infinite. So the solidly equation actually can get to an infinitely amplified system. And at all numbers between 0 and 1, you get this kind of slope, the same sort of slope that you get for curve V1. But what do you think happens? And this is like, something that I'm going to ask for your intuition on. What do you think will happen when I make R a number greater than 1, right? If it's getting sort of, stretchy and, forming a nearly flat line around a gradient of 1 to 1 in the middle between 0 and 1, and still forms this asymptote at X and Y. What do you think will happen when R is greater than 1? Does anyone have an intuition for it? Would it surprise you that it does the same thing? So between 0 and 1, we still get this flattening. And above 1, it also flattens out. And when we get to 3, is actually when it's at its flattest. And after 3, it starts to do this. So this is a really weird invariant function. And it's actually not, at numbers greater than 3, I would say it's actually completely useless. So when Andre Cronje was, I think, looking at how to implement these things, the one that he went with was R is equal to exactly 3. So what you're looking at here is essentially when this pivot point, which starts to form at numbers higher than 3, when it becomes completely flat. And this is also nice because it means that you're dealing with an integer power. So if you're doing sort of fast solutions or something in Solidity, then it's not outside of the realm of what is reasonable to be able to solve for a swap equation or something like this. Whereas if we're using numbers less than 1, then kind of fractional powers like this is more problematic. You'd probably have to create some some series to approximate the answer or something, and it gets more and more numerically unstable. Okay, so let's then ask the question, how similar are these things? I'm going to turn the curve one back on, and I'm going to start them both at 0, right? So we know that there are solutions to both of these invariants that are exactly hyperbolas. And we know that as I drive a to a higher value on the curve function, that it gets flatter and flatter in the middle and forms an asymptote to the side. And then the question is, what does the solidly function do, right? If it's behaving in a similar way, like how similar is similar? Like, can I make them equal to each other? And the answer is you can't. These are there will never be a number here that gives you the same curve on both of these functions. Which is, I don't know, like if you think that that's a surprising result or an unsurprising result, I guess is dependent on your previous experiences and so on. But to me, I thought that was, I wasn't sure what I was expecting, but I wasn't expecting it to be so obvious, I suppose. I thought that it might be the sort of thing where, the relative difference between these two curves is exaggerated at some extreme or something, but you can see that these are like perfectly obvious. The gaps between these curves are totally apparent, and trying to get these things to meet up is just a fool's errand. Okay, so that's those two expressions. And just for good measure, this Desmos, I've also got the straight line and the normal constant product one in there as well. Okay, so I didn't want to end it there. because I've actually spent a lot of time working on these things myself. So not many people know this, but when I first picked up my contract at Bancor as a researcher, my first task was to develop a product that would compete with Curve, right? Was to develop something that was attractive for stablecoin liquidity in the same sense that Curve's was. And I have never really stopped working on it. It's something that I like to come back to because, you know, I do think that there might be, I don't want to say something better because, you know, it makes it seem like, you know, that what Michael has done or what Andre has done are somehow, you know, unsatisfactory or something, which they're not. They're totally satisfactory. That even just from an academic standpoint or a scientific standpoint, I think that there is, you know, there is more room on stablecoin curves to find things that have more attractive properties, whether it be a more numerically stable, you know, invariant, or you know, something that has an easier price quote function or an easier swap function. There's just things that we might be able to do. Okay, and so what I wanted to show you was my attempts at doing that. Here, if I take away everything except the curve stable swap invariant, you can see that you know what the general profile looks like. And when I was looking at this the first time back in 2021, I noticed that it kind of has this double hyperbola type structure. So, you know, towards the, you know, the x-axis, you can kind of imagine that, you know, these two curves, you know, might be a part of one cone section. And then these two curves might be a part of another cone section. And then, of course, you've got another one down here. And I was thinking, you know, if I could just create an equation that kind of draws two hyperbolas that meet exactly in the middle, then there would be, you know, there might be something there that is that has you know, a simple solution that might mean that, you know, solving the swap equation might not be as gas heavy, for example. And this is, you know, this is exactly what that result was. And so you can see it's got a lot of the same properties that some of these other curves have. I can change the relative curvature. I can change the size the same way that you can on curve. But the other thing you'll note is that it takes two equations to do it. So yeah, you can see here is, you know, as you move these things around, you can definitely see sort of where my head was at in terms of, you know, at least defining the curvature of these things and making sure that they have a point somewhere on the invariant that gives the same gradient at the same point. But it also means that you have to implement it as a piecewise function. And that's what I've done here. So again, this is the same equation as the one that I just shown you, except that I'm only plotting one of the equations right of a certain value, and I'm plotting the other equation to the left of that value. And so it gives me the same sorts of properties, but where this stable equation differs from its competitors is that I can change its relative slope. So in the curve V1 stable and in the solidly stable, you can only achieve one-to-one swap rates. But in this case, we can create sort of arbitrary, arbitrary stable swap rates at any rate. And again, this is something that I would be, you know, happy to share with you. I think probably all of these desmoses will be included in an email that I'll send to Rabbit, so that if you wanted to explore these on your own, then you're welcome to do that. But I think that that's where I wanted to end. That's where I wanted to end everything. I hope that that you've enjoyed all of the conversations that we've had together. And yeah, I thank you all for your attention, and I'm looking forward to seeing what you guys do with the material.
Thanks so much, Mark. Amazing presentation. Tons of detail. Also really excited to see, and I really love the way you laid out the dashboards and show the difference between the two linked assets in a curve versus the two assets separate in the carbon pools. I never, I've read through the documentation, but that visualization was just incredible. I'm really curious what tool you use to put together your slides as well, because these are like, man, top notch. They're like lecture quality. It's incredible.
Thank you. Yeah, honestly, the slides I'm just putting together with PowerPoint. PowerPoint these days is extremely powerful.
They're learning from Keynote, is it? The Mac presentation app always seemed to be light years ahead, but glad to hear PowerPoint's keeping up. Awesome stuff. Any other questions? I guess we went quite a bit over, but I just was digesting all that info. Yeah, and curious if there's any of those resources that you're happy to share. You mentioned the
Yeah.
patent application, and yeah, great to see all of those invariants listed out, or invariant derivations, I suppose. I'm curious if any of the other, either your Desmos file or
Yeah.
oh no, there.
I'll
Mike's
also
got a
share
question.
this. So this is something else that I'll share with you guys. So I'm currently in the process of productizing this, but this is basically this is all of the information that you would probably ever want to know about constant product bonding curves and concentrated bonding curves. And so I put this all into like a single package that we can use to sort of investigate how different AMMs perform under different conditions. So for example, if we were to look at two assets, let's look at compound and Aave, for example, let's say for the last year. So what I'm doing here is I've constructed an API call to three different data sources. So I've got API keys both to crypto compare, CoinGecko, and CoinMarketCap. And the thing that this lets me do is fetch data at any frequency. So I can do minute, hour, or day. Minute I think is only stored for the last 7 days, but whatever. What it does is it will pull them in the same numeraire, so usually USD, and then it stitches them together so that you can get a candlestick chart for any asset versus any other asset. And then after that, you can simulate what one of these would have been used around. So something like this, for example, we can choose for Uniswap. We can also choose different ranges for carbon. So we can move these things around and decide what these things are going to be looking like. There are a couple of other things we can do with carbon that we haven't sort of discussed. You can change, for example, the portfolio composition, which is something that you can only do when in carbon because it's got like different dimensions. We can choose protocol fee levels and which protocols we want to simulate, which animations we want, and how to put them, that kind of thing. And so, yeah, this is, fundamentally, it's meant to be a financial tool. But, at some level, it's also just, like a textbook now of bonding curve, bonding curve theory. So, each one of these functions kind of represents a certain component of amplified or concentrated liquidity. And, just to see how some of these functions operate and, how to analyze them, I think would be something that you guys might get a lot of value from. And I'm very happy to share this stuff.
That looks awesome. Yeah, I would love to play around with that. And it's too bad Sean is out and about today because I know he's working on some dashboard stuff or has been working on dashboard stuff in the BCRG. So I'll make sure he catches this recording because I think some of these things would be amazing to pour through with the technical literacy as well. Mike, do
Indeed.
you have a question?
Yeah, thanks so much, Mark. Outstanding, and I appreciate your time, your dedication, your excellent explanatory. Just for this one question, what's your take on Curve's new Curve USD type of system design? It seems to be um, pretty cool in how it's changing that whole liquidation experience and offering
Yeah.
to DeFi. Anyways, thank you, Mark.
You're very welcome. But yeah, no, my take on it, I'm a very big fan of pretty much everything that Curve does. Curve V2 wasn't, I didn't like Curve V2 very much. But yeah, Curve V1 and their Llama lending system is beautiful. The idea of and the way that they've implemented it so that you can sort of be unliquidated, you know, if your collateral sort of regains value, is extremely interesting. Yeah, I haven't had the time to sort of really sit down and digest it. So like I don't feel like I've got the level of erudition required to sort of speak with authority on it. But at least from the outset, I'm extremely impressed with it. I think that it's exactly the level of creativity and you know problem solving that Curve has kind of incorporated into their brand. So it's yeah, it's an extremely impressive piece of kit. Oh, and our simulation just finished, so you can see here that we're actually you know generating these plots and things. But yeah. I can't see
Awesome.
if we've got
Well, I'm
any.
sure there will be a ton of follow up questions as we pour through some of the content from the last few. We've actually talked about yeah packaging or taking out snippets of some of these talks and being able to push some of that information even further. So hopefully yeah we'll be able to continue and or have some follow up on perhaps questions or I mean further advancements in these tools. It's amazing that even in just the past few years, there's been so many experiments and, as you say, so many re-applications of the same invariants. Yeah, I'm curious where the new use cases, where new contexts will you know push further evolution of these tools. Did you have another question, Mike, or is your hand
I
just still up
did.
from
I
last
did.
time?
I'm sorry for being for hogging. Mark, one more question. Are you familiar with a protocol called DOPEX?
Yeah. Yes, I am.
What's your thought on their new? They call it CLAM. They're utilizing Uniswap's V3 by providing option profiling at each bin in the concentrated liquidity that V3 offers. It's really cool. They had an MVP out where they let users test it out with just the ARB token, but it could be a really interesting like derivative to entice liquidity and utilize liquidity that I guess would just sit dormant.
Yeah.
If you don't have any thoughts, all good. It's pretty fresh, but I just wanted to throw it out there.
Yeah, I thank you for telling me. Because I wasn't aware. Did you say it was called CLAM?
Yeah, I didn't make a mistake. They call it CLAM,
Okay.
CLAMM. It's kind of like concentrated liquidity automated market maker.
Got it. Yeah, look, I don't know. I wasn't aware of it, but what I am aware of are other like quadratic option pricing models. So the people that really pioneered that you know this space or the idea that you can write an option on top of an AMM. And what I mean by that is, you know, like full Black-Scholes style, or, you know, fair options pricing. The first project to do it successfully was called Squeeth, or Squared ETH. And I highly recommend reading
Incredible
the
product,
documentation.
Mark.
What's that?
I said incredible product, man. Squeeth is
Yeah,
that
remarkable.
power perpetual, unbelievable.
Yeah,
You
really
get 2x
remarkable
ETH
product.
with no liquidation. Yeah, it's really it's not available for US residents, just if anyone's a citizen. It just changed in the last about 6 months.
You might also be familiar with Guillaume Lambert's product, Panoptic. Have you heard of Panoptic?
No, sir.
Okay, so Panoptic, I definitely recommend you should learn who Guillaume Lambert is and read some of the stuff that he's produced. So he actually has he's shown that there is a way that you can treat options pricing that basically approaches Black-Scholes on a under some conditions. And what he did was to create a full options protocol built exclusively on top of Uniswap V3. It wouldn't surprise me if the Clam product is at least inspired by some of the work that Panoptic has done. But it's similarly impressive.
Wicked. I'll look into that. Thank you, Mark.
Yeah, my pleasure.
And how did you spell that? Squeth, was it? Squeeth? Skeeth?
Squeeth, yeah. Yeah, so they actually have a formal proof of it's equivalent to Black-Scholes, but non-linear. Yeah.
Ooh. Nice. Pull these links from the Twitter as well. If anybody wants to follow that, they're Panoptic XYZ. Just drop the link in the chat here if I can copy it. Good stuff. Awesome. Any other questions, or should we wrap it up and then save more chats for next time? I'm sure there'll be lots.
I'll share everything with Rabbit again via email, and so I'll let him distribute some of the material back to you guys. But anyone who wants the simulator that I just shown, reach out to me directly.
Sounds great. Thanks so much, Mark. Great presentations, and looking forward to having you back for another set.
Wonderful. Thank you so much, everyone. I hope that it was useful.
Yeah, definitely. Super inspiring.
Thank you so much.
Great.
Thank you so much.
Thanks, guys.
Have a great day, folks.
Catch y'all again soon.